Checking how the microphone works. Okay, cool. So it's recording now. I'm David. This is a revision seminar for Advanced Math Echo 3 in 2015, those of you watching in the future. I put in my disclaimer now that I'm hoping I'll be helpful, but I really only learned, or at least looked at some of these things today. But that is how it works in the Maths Learning Centre sometimes. So, right. So I've been asked to talk about two things that are specifically in the exam, because your lecturer said that they were. And by two, I mean two large sections. So the lecturer has said needs to know how to do an optimisation problem, especially a Cobb-Douglas-y sort of thing, as far as I can tell. And there's all these terminologies named after people that I've never heard of before that are apparently important, and so we'll go and find out what they are. There are different problems which have a three-letter acronym apparently. So UMP and EMP, which we will try and figure out what they mean. And someone's also asked about the contraction mapping theorem, because I believe the lecturer specifically mentioned that too. Alright. Okay, so we'll see what I get up to. And anything else come to Maths Learning Centre. And I should say now, for those who are listening, the Maths Learning Centre is designed to help people learn how to learn maths, and any particular topic is not necessarily something that we know about. So I put my disclaimer in again, that's what I'm doing here, trying to figure it out. Hopefully by seeing someone try to figure it out, you can do it yourself and learn how to figure it out as well. Okay, now I do need this here. So, I have some notes from one of the students, not going to say your name on the recording, and they are lovely, but they seem like they're from an old version of some of this course, rather, because they have a lot of other stuff in them too that you have in separate handouts elsewhere. So that was a bit confusing. And they are all the notes we have on this optimisation section. Okay, just making sure I know where I stand. Okay, so does anyone have any particular things that were worrying to them about the stuff that was in the optimisation bit of the course? As a place where I could start.
The Slutsky equation.
Slutsky equation? Sure, let's start there. Let's see what we can figure out from that. I'm trying to sharpen my pencil, and my pencil sharpener has decided to break. So.
Is the tutorial particular for a specific question? So you can go for a specific question? No.
Yeah, but we didn't get the question, so we didn't know what she was asking. She just started, oh, that question one.
So no one has those questions? Sorry? Okay.
The best we can imagine is that, like, we'll be given some function and it'll say
some Cobb-Douglas.
Yeah, some Cobb-Douglas utility function, maximize utility, and then, you know, show that the Roy's identity holds, show that Shepard's lemma is a thing. And then presumably show that Slutsky equation holds, although I'm not certain Slutsky's equation. Like, I know what it is abstractly, but.
So the notes mention a Hicks-Slutsky equation. Is that the same thing?
Yeah,
I would say.
This is what the notes say. Hicks-Slutsky equation, compensated demand. No?
Yeah, that's it.
Okay. Alright, I'm going to read this. It can be shown that the compensated demand at utility U0, i.e. HI, P1 up to Pn U naught is equal to the uncompensated demand at income E P1 up to U naught, i.e. xi P1 up to Pn E P1 up to Pn U naught. This result is known as the duality theorem. Thus, totally differentiating that identity with respect to pk, we obtain this, which by Hotelling's theorem gives this, and so this. These are the Hicks-Slutsky equations. So these last two, I imagine, are the Hicks-Slutsky equations?
I think it's the last one.
The last one.
Well, that's the one you might seem to focus on in the lecture.
Okay. They are, of course, not significantly different because the other one's just got one move to the other side. Okay, so in order for me to understand this, I'm going to need to figure out what all of the notation means. Okay, so I'm just going to write down this and see if I can go find the notation. Nope. Alright, so Slutsky equation. Have we got any thoughts that I need to take into account here? That's really useful if you've got any.
So
It's not there.
Yeah, you can't.
That's totally not working, is it? It's like there's nothing there.
would you like to borrow a pen? What does that mean?
I'm just going to write them. No, I need to do it here. I don't know how to change. Is that better?
There we go, yep.
Right. We've got something. I wonder if we turn on these lights again, whether it might actually... No, that's worse, isn't it? Alright, turn them off. In the dark for me. Okay, so we have the Slutsky equation, which has these things. So this was compensated. Which was that is equal to uncompensated income which is xi pn e blah blah blah. Okay, I would like to attempt to understand what that means, so I'm going to go back a bit and see if I can find the useful information about that. I really thought I'll go into the nice new building, but I really should have just done it in the Bragg, in the Darwin West, which is older, but the document camera works. Okay.
That's from lecture assist.
I'm on page 41 of these notes, of these printed notes. Let us consider the maximization problem number 20. Recall the maximum over the x's of f of x1 up to xn, also a1 up to ak, subject of g1 blah 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 equals c1, gm blah blah equals cm. Again, let x1 up to xn, lambda 1 blah 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 be the Lagrangian quadrant. What are these a's? The x's are supposedly the variables we're interested in. What's the difference between the x's and the a's?
Checking. They're the prices. They're equal to the prices.
So in the context of demand and Slutsky's equation, the a's are the p's?
Yeah.
Oh, I get it. Maybe.
The parameters. And the x's are the variables.
Okay. Can I look at that? Okay. I'll take that. Are you going to write in this? So I tried very hard, but there was a lot of notation, so I need to talk about it to try and figure it out. So this is all related to this envelope theorem. We've got Lagrangian with a whole lot of different lambdas, one for each of the constraints. So these g's here equals the c's, they're the constraints. And we've got that. But x star a1 up to ak, x star n a1 up to ak, and lambda 1 a1 up to ak, and lambda m a1 be the values of x and lambda that solve this problem. Okay. Right. So the a1 up to ak might be like the prices in my budget constraint, which for any particular problem would be fixed. Okay, so I think I understand this. So we've got the x's. Normally in these problems you go, well, I want to find the bundle of x's that maximizes whatever this function is. And these are some parameters which normally, if you knew what they were, you would just run from that and you'd figure out the x's that maximize the problem. So they might be the prices of things. Only sometimes you want to figure out, well, what if those parameters were different next time? How would I solve the problem then, and what would the solution come out to be? So maybe we could conceivably do all this working with just a's or p's, and then they say this is the answer, and we could skip all the Lagrange stuff and go straight to the answer next time we got a different set of a's. It's a little bit like going, well, let's find the maximums and minimums of y equals x, x plus 1, x plus 2, and then saying, well, what would it be if it was x plus 2, x plus 3, or x plus 4, x plus 5, and I could just put it in with a's and b's for those things there and see if we could figure out a formula for it. Okay, so now v, v is the f of those x's that maximize the problem. So it is actually the actual maximum. Okay, I'm almost at the point where I can draw a picture for myself that might make sense of this. So, the envelope theorem says that the derivative of v is equal to the derivative of curly L at the maximizing values. Right. Okay, I'm going to start there. I'm sorry, this is apparently related to this. So, alright. Since I've talked about it, I'm going to try and figure this out. Just going to come back to that later. The envelope theorem. See if we can say something about the envelope theorem. Now this is all relating to this whole Lagrange method of optimization, which goes, what you have, this is not necessarily the same description as what's here, so you need to translate, but in my head I'm thinking there's some sort of situation described by parameters a1 up to ak. So that a1 up to ak, I think it was k, yes, they describe the situation. So perhaps they describe the prices of the various commodities, or they describe various other things to do with the situation. And then we also have some sort of utility or profit or some sort of decision thing that we want to maximize or minimize. I'll stick it with maximize, which is F, and that depends on various inputs, which are the X's. Is it N?
Yes.
Okay. Cool. So that function will have some sort of formula that will involve both the parameters and the inputs. But philosophically, the parameters, you don't generally get to choose whether they change or not. And the X's, you get to choose whether what your choices are for those. So the X's might be, the A's might be the prices of things, which may change, but you don't get to choose whether they change and how much they change by. And the X's are how much you buy of those commodities, but which you do get to choose. Okay, so I think I've got it now, that the A1 up to AK, we don't get to choose those. And the X1 up to Xn, we get to choose. And together they produce a function value of some sort. Oh, Xn, does he put a semicolon there? Good, that makes sense to me. So whatever the function value comes out to be, maybe it's profit, maybe it's your personal utility of how you decide whether things are better or worse. It will depend on both the things that you chose and the things that the world chose for you. But all of those, if you're in a different situation, which is what the AK's changed, then the F would come out to something different. And if you chose a different response to that situation, which is what the X's are, the F will come out to something different. Okay. And so the philosophy is that in response to these A's, you choose some X's and then you get a function. And your question is, how much does that, how can you figure out what the correct choice of X's is given the situation A's, the A's from the situation, what is the correct choice of X's that gives the maximum or possibly minimum value of F? Okay. Subject to, but there may be even more things about the situation which you need to take into account, which would be the constraints. So this would be unconstrained at the moment. It's just, this is the deal. And then there will be further things which are the constraints, which constrain what X's you're allowed to choose. Okay, so I don't get to choose the A's, they are whatever they are. I do get to choose the X's, and if I can choose whichever X's we want, that's unconstrained. But if I have to, other than being positive usually, that doesn't usually count. But if I have to choose the X's according to some sort of system where they have to add up to something, or there's various other things that they have to satisfy, then they're the extra constraints. So may have to choose the X's according to some constraints. And those constraints usually take the form of functions of themselves. And so you'd go, well, just a second, you're only allowed to choose the X's so that this function comes out to a specific number. So they have numbers too, don't they? Etc. Okay, so this is what I'm thinking. In my head, I'm thinking that this might be all the possible X combinations of X that we might be able to choose, and then within it, these are the ones where G1 of the x's and the a's comes out to C1, and maybe these ones here are the ones where G2 of the x's and the a's comes out to C2, and then here are the ones, the only ones we're allowed to have, and you can, each constraint will narrow down the amount of x's that you're allowed to choose, and then you're only allowed to choose the x's within here. That's my concept. And then each of those x's will produce a value for f, and you want to find the one that gives the biggest value for f. So that would normally be a 3D picture with the height being the value of f. So these functions here, as these g's, they're not technically, I don't need to think of them as function values. I think of them as describing regions in the plane. Okay, cool. I'm just talking through my understanding of it. I hope you don't mind. Okay, so then it says that suppose you go through this world. So the way that you would do this is you'd go curly L is f plus lambda 1 of G1 minus C1 plus lambda 2 of G2 minus C2, etc. And what I've done is I've shortened what's written there. We just have to remember that f is actually a function based on the x's and the a's. G is a function based on the G1 is a function based on the x's and the a's. G2 is a function based on the x's and the a's. And the lambdas are variables, and the c's are constants. So, have I got them around the right way? Crap, got them backwards. Sorry, C1 minus G1. Not that it should make a difference to the answer, but just want to be consistent. Okay. So, I have left out all the bits with the brackets. So normally there's a bracket with stuff in it here. So that bit that I've just squiggly bit there that's all of this stuff here, x1 up to xn, a1 up to ak. So it's just, this is just my picture of it so that I don't have to write all of those bits to figure out what's going on. Okay, I just need to remind myself which bits are functions and which bits are numbers. And then you'd go through the process of doing all the derivatives and getting rid of all the lambdas, and you'll get a solution. Okay. Right. Yay. And you'll get a solution, and then the solution says, oh, my computer's turned itself off. My solution is, right, that we get a whole lot of, we get the correct x1 up to xn and lambda 1 up to lambda n to maximize f. Okay, that's our solution. Doing well. And the correct x's have stars attached to them to remind us that the original x's as we wrote them were unknown variables. We didn't know what they were. But now they are specific values of the variables. For the lambdas, apparently you don't do that because you made them up for your own purposes, so they are just whatever they turn out to be. Now, here's the thing. So here's the philosophy. You maximize V, and the actual maximum value of F, maximize F, and the actual maximum value of F is V. Yep, I think I've interpreted everything so far in the theorem set up for this theorem so far. Right. Now I would remember that the maximum value of f is v because v is the voiced version of that consonant. I don't know if you know much about linguistics, but some letters you use your voice box and some letters you don't. And f and v are the same sound, but f is not voiced and v is. You can't hum with an F, but you can with a V. So doesn't work, okay? So they're the same sound, but this one's got a voice. I don't know why, but that would be how I would remember that, why it's chosen as a V. I would have chosen M for maximum, but that's just me. Okay, so here we are. So let's just have this picture here. We had our situation, which was described by the A1 up to AK. They described the situation that we were in. Okay? And according to that situation, and our constraints and our function, okay, the A1 up to AK, right, produced an x1 star up to xn star, and a lambda 1 up to lambda n, and a v. Right? And if I was in a different situation, I could go through exactly the same process and produce a different x1 star up to xn star and a different lambda 1 up to lambda. Sorry, that's not n, is it? How many constraints are there? M. Sorry. And a different v. So in a different situation, I would get a different maximum value. Okay, if the prices were different, I would get a different profit. And so therefore, v is a function of A1 up to AK. That's the concept here. So we've switched our philosophy, right? No, well, not quite, but we don't get to choose what A1 up to AK are. But we do know that even if the world chooses them, different choices will produce different values for v. And so v will be a function of A1 up to AK. Right. And being a function of A1 up to AK, that would mean that I could say, well, if A1 was changed by a bit, how much would v change? If I changed the situation, how much would the maximum change? So even though I have no choice as to what A1 up to AK are, I could say, well, if the world changed the price, what would be the new maximum? If I made the best possible choice, if the world changed the new price and I made the best possible choice, what would be the new maximum that I could possibly get? And you could figure that out. And so you could know how much v changed when A1 up to AK changed, and that would be a derivative. And just because we seem to have run out of letters because we already used I for something else, we will use dv over dh for the various values of h. We can find the partial derivative of v with each of these. We can say, well, if the world changed this one here, it's somewhere in the middle, what would happen to v? Would it go up or down? And how much by? And that's what we can find. And the envelope theorem says that that's the same as differentiating the Lagrangian. We'll get the same answer. So, the envelope theorem says, I do not have to find out what the maximum actually is to know how it will change when the a's change. Because all I have to do is differentiate the Lagrangian.
Wait, could you say that again?
I do not have to find out what the maximum is, though technically all you have to do is, I just know that that the way that it changes will be the same as the way that the Lagrangian changes. So if I don't have to differentiate, I don't have to find a formula for v in order to know what its derivative is. I just have to find a formula for L and differentiate that instead, because it has the same derivative. magic trick, really. Not that I know why that's important, but that's apparently the truth. So I'm working entirely off of these notes. So we can find that, but it's the same answer as that. Yes. Or at least it is at the same, if you're using the values of x and lambda that go with having the maximum. Yeah.
Also, b is also like a function of lambda.
No.
But then when we take the derivative of...
Just wait.
Yeah, sure.
As long as you use x1 star xn star lambda 1 up to lambda n. As long as you use those. So it really doesn't give us all that much, because we would need to know, the only difference between knowing these and knowing v is subbing all of these back into f, but it doesn't matter. Okay, so I'm just interpreting what it says. Okay, no idea why, but or why this is important, but that's what I have. Right. It may be useful for some approximation sort of thing, but I'm just doing my best here. I just want to make up an example to try and figure out what the frill is going on here. So let's see if I can see what's going on. So let's say maximize. That's a Cobb-Douglas, isn't it? They have to add up to 1? Is that how it works?
They don't necessarily have to add to 1, but they change that.
Well, I'm just going to make them add to 1. Does it matter? Does anyone care? I'm just going to leave it. Maximize that. I'm just going to pick some numbers if that's okay. I'm going to choose 1/4 and 3/4. Is it normally M that we use in that spot?
He makes us use W.
Sorry?
We would usually use M, but Dimitri uses W either way.
Just to dubs it down. Cool. We used M to count how many constraints there were. Going to have to start using Hebrew letters soon. Okay. Alright. That's the problem. I'm not actually going to see this as like an exam problem at the moment. I'm just going to work through this with this. So we only have one constraint, which is the budget constraint. My situation is described by the P1 and the P2. They are my A's that's being referred to. If I had a specific P1 and P2, I could conceivably figure out the actual answer to the problem. But what I'm going to do is I'm going to attempt, and I suppose W is technically one of the A's as well. It describes the situation as well. So, okay. And then I'm going to, so what you would do is that you'd set up your Lagrangian. So my utility is my F. And then we'd have a lambda. If I had multiple different constraints, I'd have a lambda 1 for the first one and a lambda 2 for the second one. But since I've only got one, I only need one lambda and I don't have to number it. And so we would go number minus the function. Like that. Okay? And that would be my Lagrangian. And then in order to solve this, I would do dl on dx1 and dl on dx2 and dl on d lambda. Okay. And what does this notation you had in your notes FOC stand for?
First order condition.
Which is what I'm just doing now.
Yeah.
Okay, right. I couldn't figure it out. Okay. Sorry?
Oh, it was like a couple of weeks in intermediate micro where I didn't know what FOC was. And I just kept using it everywhere. I'm like, cool.
Sometimes it's FONC.
Yeah, Jake does that FONC, first order necessary conditions.
Ah.
Just to be.
Yeah, I have a t-shirt that has TLA written on it, which stands for three-letter acronym. Because they're everywhere.
You obviously get these printed.
I make them myself,
Yeah.
so you get t-shirt transfer paper. This is a frustrated cone, which is the name of the shape of a cone with the top cut off. So this is technically a frustrated cone. Because it's a frustrated cone with a frustrated expression. Okay, anyway, so dl on dx1. So everything other than the x1 counts as a constant, right? So the x2 to the 3/4 counts as a constant and it's multiplied on, so it will still be there after I differentiate. And that's a times sign, not an x. And then the x1 to the quarter, the power will come down, and then the power will come down 1 by 1, which would make it minus 3/4. Okay. Now this bit here, the lambda is a constant which is multiplied on there, so it will still be there. The w is a constant, so it will vanish. The minus, that will still be there as well. P1, x1, that will become a P1. And then P2, x2, they're both constants, and so we haven't got any x1s there, so I get a 0. Okay. And so that will be 1/4 of x2 to the 3, x1 to the minus 3/4, x2 to the 3/4, minus P1 lambda. Okay? And partial d on L on partial dx2. So this time x1 counts as a constant, x1 to the quarter is a constant, so and it's multiplied on, so it will still be there afterwards. x2 to the power of 3/4, the 3/4 will come down, and then 3/4 will go down by 1, so it's minus 1/4. Lambda is a constant multiplied on. W will come out as 0, the minus will still be there. P1, x1 will vanish because it doesn't involve x2, and P2, x2 will leave me with a P2 when I differentiate it. Okay. So I get 3/4 of x1 to the quarter, x2 to the minus 1/4, minus P2 lambda. And then finally dl on dx2 will give me the budget constraint back again, because I know that always happens. But just for completeness' sake, that doesn't involve lambda, so it will vanish. Lambda, this bit here is a constant multiplied on, so it will still be there afterwards, and the lambda will become a 1, so we're just going to get w minus. Alright, and the first order conditions are that those three things all have to be 0 simultaneously to get our maximum.
Is that last one we just explained that?
Yes, you are completely true, because I already did x2. Lambda. Okay, sweet. I wonder if Lagrange used L and lambda. Because lambda is a Greek L, so he just used his own name. Or whether other people used it later because to name it after him. Because it would be sort of a bit cheeky to label everything by your own name.
Dividend we're always doing with respect to labour. So you get like to remove L with respect to L.
Interesting. Okay, and so we need all three of these to be 0 simultaneously in order for this to work. it seems in everyone else's working that it's necessary to say that that's what you've done, first order conditions. So I thought I would put them in. And I don't want to say FOC because I'll forget what it stands for. So, okay. So, then we have to, so we've got three equations in three unknowns. The W and the P1 and the P2 don't count as unknowns. I don't know what they are, but presumably someone will one day tell me what they are. So I don't have to figure out what they are. So I need to figure out what x1 and x2 and lambda are in terms of the others. I don't usually normally have to know what lambda is, but for the purposes of the envelope theorem I do. Okay, so let's see. I'm going to number them if you don't mind. Number 1, number 2, and number 3. So there's lots of ways to attempt to solve equations that are like simultaneous equations like this. Normally you work with the lambdas first, that's usually the MO in this, and sub everything into the last one later. And you try and arrange them in such a way that you can make the lambdas go away. I have two approaches that I could try. I could multiply the top one by P2 and the second one by P1, and then the bits with lambda would match, and I could subtract them to make them go away. Or I could get lambda equals for everything, and since they're both equal to lambda, they could be equal to each other. Or I could get lambda equals to everything and divide them. Seems like a good approach to at least put the equals, the P1 lambda on the other side as a starting point, so I'm going to start there. So from number 1, I've got a quarter of x to the minus 3/4 x2 to the 3/4 equals P1 lambda. And from number 2, I have 3/4 of x1 to the minus 1/4 x2 to the plus 1/4. No, sorry, that one's a plus, that one's a minus. Equals P2 lambda. Alright, so that's what we've got so far. I've just moved this over to the other side, that seemed like a good idea. So at this stage, I could divide this one by P1 to get equals lambda, and this one by P2 to get equals lambda. And since they're both equal to lambda, I could make them equal to each other. Or I could go, say, this equation divided by that equation, and that would make the lambdas disappear as well, which is a classic approach that lots of people use.
1 over 2.
Sorry?
1 over 2 or
It doesn't matter. But there's probably a better choice, but I don't know what it is. So, because usually you write x1 in terms of x2, or x2 in terms of x1. No one cares. I would do them in the order they are currently presented because that's easier at the moment. Okay, so let's see. If I go divide them, this divided by that is what I want to do. So 1/4 divided by 3/4 would be 1/3, because the quarters will cancel. x1 to the minus 3/4 over x1 to the plus 1/4. When you divide things with the same base, the powers subtract, so I'm going to get x1 to the minus 1. And x2 to the 3/4 minus x2 to the minus 1/4. When you divide, you'll subtract, so you'll get the powers. 3/4, subtract the powers. 3/4 minus minus 1/4 would be plus 1. And so that's where I am at the moment. One of the nice things about these Cobb-Douglasy things, especially if they add to 1, is that at this stage you'll always get something times x, one of them to the minus 1, the other one to the 1, because of the way it's set up. But if they don't add up to 1, it'll be whatever they add up to, that the power is. And there we have it, something. We've got something at least. I don't know what we're supposed to do with this at this stage, but I'm just going to run with it. I don't like that third being there, so I might put it over that side. So x2 over x1, that's what x2 to the 1, x1 to the minus 1 is. That looks particularly simple at the moment. And I could therefore figure out what x2 was in terms of x1 at this stage if I wanted. So x2 is 3 p1 over p2s of x1. Yay! And then I would attempt to figure out what x1 and x2 were in terms of p1 and p2 and w. Because currently I figured out what x2 is in terms of x1, so I could conceivably sub that back into number 3, which is the same as subbing it back into there. Because number 3 is just that thing rearranged. So, let's see. Sub into number 3, and we get w minus p1 . So what I've done is I've replaced x2 in this formula here with that version of x2. So whenever you see an equal sign, you can always replace anything on one side, anywhere, with whatever's on the other side. And luckily the p2's cancel, and I get w. So what's that? p1 x1 and 3, so 4 p1 x1. So that can go over this side. And then if I divide both sides by 4p1, I'll get x1 is in fact w over 4p1, which is awesome. And so therefore now, if I put this back over here, I can figure out what x2 is. (3p1 over p2 x1), which is 3p1, over p2 times w over 4p1. They cancel. 3w on 4p2. It's kind of cool, like the 3/4 that was originally attached to the x2 in the original formula has ended up next to my fraction.
Cobb Douglas does a lot of like really convenient things.
Sorry?
Cobb Douglas does a lot of like really convenient things. I think we just use it because it's...
Yeah. Convenient.
Yeah, basically.
There's a lot of that going on in science, generally in economics in particular, if you're allowed to call it a science.
I don't think we qualify for that sometimes.
Sorry?
I don't think we even qualify for social science sometimes.
Faculty of Professions used to be the only faculty without sciences in its name. In our university. But we used to have a Faculty of Humanities and Social Sciences, but they've changed it to Faculty of Arts. So now you're not the only one without sciences in your name. You should change your name to Faculty of the Professional Sciences just to mix it up.
Science of teaching and architecture.
X1. So what have we got? Just to summarise, what was X1? W on 4P1.
Yeah.
And X2 was 3W on 4P2. And those are the x's that would produce the maximum value of my function.
So they'd be like an x1 star and x2 star.
In fact, they are exactly x1 star and x2 star. Technically, there's a lambda that goes with this, which we didn't actually figure out. We didn't find that lambda. So we could, if we wanted to, find that lambda. If all we wanted to do was find the x1 and the x2, and we didn't want to prove that the envelope theorem is working properly, we wouldn't need the lambda. But to do the envelope theorem properly, we actually have to know what lambda is. So I'm just going to do it anyway. So normally you wouldn't find lambda, but we could find it. So we could go back and find an equation that has one of them in there. So I could go back to, say, number 1. Or maybe this one just here even. That one there. That's got a lambda in it. And that should tell us what lambda is. I'm going to call this one number 4 if you don't mind. So let's see. So from number 4, x1 to the minus 3/4, x2 to the 3/4 is p1 lambda, and so lambda equals so what I've done is I've divided both sides. Oh, that's nice. I like this shadow. That makes it easier to read. I have divided both sides by P1, and because the 4's on the bottom, I've just put it in there. If I was being very clear-headed, I could possibly put the x1 here on the bottom as well. Actually, that would be really cool, because I actually know what x2 on x1 is from one of my previous equations. So that's kind of nice. I'm just going to do that. So being a negative power, it goes to the bottom and becomes a positive power down there. And I'm just going to, that on 4p1, I'm going to pull that out as a fraction, 1 on 4p1. And these two things both have the same power, and powers can distribute and whatever the opposite of distribute is over division. So because they're both the same power, that power can come out of the division. And the reason I have done that is because elsewhere in my working, I know what x2 over x1 is, so I can sub that in. If I hadn't had that, and I just knew what x2 and x1 were, I would have to sub them both in separately. But that's more work than going back and finding x2 over x1, which I happened to notice was there. If I didn't happen to notice that, I would have gone and I would have put x1 star and x2 star in there. So x2 over x1 was 3p1 over p2. Now I could simplify that if I really chose to, but that is the correct value of lambda to give the maximum. So, what the envelope theorem says at this time here is that I could figure out the maximum value of f So the maximum value of f, actually I will do a colon, is what they call V in the envelope theorem. And to get that, I would sub in my x1 star, my x2 star, and well, I don't need the lambda, but I would sub in my x1 and my x2 star into the formula for f. So I go back to the original and I'll go, look, the whole idea was for us to maximize this formula. And I've now found the x1 and the x2 that actually do that. They do maximize the formula. And so if I sub them both into this formula here, it will tell me what the maximum value of the function is. So, oops, sorry, it's not f, it's called u in this particular problem. And perhaps that's why he's chosen a v, because it's the next letter after u. And it's traditionally a u in the stop. What's that?
I think, and please don't quote me, but it's V because it's indirect utility.
Okay.
So it makes more sense if you're doing economics, but I think, I hope.
Yeah, so this is what the utility would be if I had chosen my personal maximizing x1 and x2 under the situation that I'm in.
Yeah.
And is that what indirect utility is?
Yeah, it's
Yay.
just the reverse.
Okay.
And we've always used V for it, so that's why
Because it's the letter after u.
Yeah.
So x1 star was, let me go look that up, w on 4p1, and x2 star was 3w on 4p2. So that in fact is the maximum value of u. Given this particular situation of having P1 and P2 and W as my prices and budget. And I could conceivably simplify that, I suppose. Because powers expand out over both division and multiplication, I can do that. Let's see, the whole top line, because it's all, can be multiplied together, I'll get 3 to the 3/4, whatever that is. W to the quarter times W to the 3/4. When you multiply things with the same bottom, the powers add, so I'm just going to get a W to the 1. 4 to the quarter times 4 to the 3/4 is just 4. And that's what I get. Not pretty, but there it is. So, the envelope theorem says that the derivative of v with respect to p1 and p2 and w will be the same as the derivative of L with respect to P1 and P2 and W, as long as I sub in the correct values of x1 and x2 and lambda. So to check the envelope theorem...
What problem was that?
Sorry?
Sorry, you just say that all the time. The envelope, like what the envelope?
The envelope theorem says that dv on dp1 will be the same as dl on dp1 at x1 star, x2 star, and the correct lambda. And also for p2, and also for w. Sorry. So it will be each of these three derivatives will match at x1, x2, lambda. So I'll just do one of them if you don't mind, rather than all of them, but that's what the envelope theorem is going to say. So let's see if it works. So, V is equal to this here. So if I did dV on dW, everything other than the W counts as a constant, and so it's all just a constant multiplied by W, so it will be 3 to the 3/4 over 4 P1 to the quarter, P2 to the 3/4. That's dV on dW, partial dV on dW. And let's look at dL on dW. Go back to my L, which was here. That's my L there. Really hoping this is correct. The world will make no sense if it's not. So let's see, that doesn't involve a W, so that will disappear, because I'm differentiating with respect to W now. The lambda is a constant, it will still be there afterwards. The derivative of W is 1, and the derivative of that is 0, so that's just going to give me lambda. So if I go and look at my lambda, the correct lambda was, oh my goodness, it's the correct answer. Except possibly I may have gotten something, no, it'll work. Ready? So the correct lambda is, the correct lambda was 1 over 4p1, 3p1 over p2 to the 3/4. Are you ready for the magic trick? I will expand out my 3/4. Now let's see. P1 to the 3/4 divided by P1 on the bottom would give me P1 to the minus a quarter. I think I might have done something wrong somewhere then, hey? No, that's okay. Nope, it's alright. So I'm going to get, that is still there on the top. P1 to the 3/4 divided by P1 to the 1 would be p1 to the minus a quarter. On the bottom, I've still got a 4 and a p to the 3/4. And now if I move that p to the minus a quarter to the bottom, I'll get 3 to the 3/4 over 4 p1 to the quarter p2 to the 3/4, which is exactly the answer I should be getting because it's the derivative of dv on dw as well. Yay! Okay, so that's apparently the point of the envelope theorem. That's it working out in math, in algebra. I don't know what it means economically, but that's what it is. So dl on dw was lambda, which happened to come out to the same answer as dv on dw. Okay. Right, now I think I understand that theorem. The whole point of me looking at that was to attempt to figure out what Slutsky's equation is trying to do. So Slutsky's equation is specifically referring to an economics sort of thing, isn't it?
Yeah, but it's supposed to be a specific application of the envelope theorem.
Yeah.
Slutsky's demand elasticity. It's about the substitution of income effect.
Yeah.
Okay, so it's about, it says here that we get it from Hotelling's theorem.
If it's any help at all, the description, like the reason for Slutsky equation we were given is when we are given a function and we say, all right, maximize this function, and then we're like either a utility function and we're given another function, and then we say, all right, reverse it, do the expenditure on the top of what would have been the constraint and minimize that, to minimize your spending in order to get to a certain level of utility, you can use Slutsky's equation to show a connection between those two solutions via their derivatives. And that's all we got.
Okay.
We'll ignore that. Yeah,
So let me just see if we've got this right. Given a particular situation, an economic sort of situation which has a utility and an expenditure, which is your P1, X1, etc. Okay, making sure I've got this right. Okay, so Slutsky then, we've got a utility, u, which is some function of x1 up to xn and p1 up to pn. Yeah? Presumably. Okay. And we have sort of expenditure, which is sort of your p1, x1, like that. That's not a comma, it's plus. So it's the total things amount that we spend, yeah? And so your classic utility maximization problem is to maximize this, subject to this being equal to a specific amount. Yeah?
You won't be, yeah.
So it's maximize u, I shall call this E, subject to E being equal to a specific amount. Yep? Which is traditionally called W. Or Y for God or anyway.
And if it helps with the notation, the solution gets evaluated with x's, whereas when we do the expenditure minimization, we get h's.
Okay.
Which just might make a bit more sense than my other notes.
Yep. And so solutions are called x1 star up to xn star. That's what we normally call the solutions to that. Okay, good. And then the expenditure minimization problem is that we want to minimize the expenditure subject to the utility is some specific amount. Okay.
Yeah. So the solutions to that are H1 to Hn.
And those are the x's, the solutions for x.
The h's are supposed to be the same as the x's, I believe.
Or
Yeah.
like related, kind of.
Yeah. Okay, but they go in the positions of x in the formula to figure out what the expenditure actually is.
Yes.
X positions. I mean, these obviously go in the x positions because they're called x, but I just wanted to make sure that I knew what was going on here. And so, under that original philosophy, where remember that this is the situation is described by these p's. Okay, the situation is described by the p's. They are the a's in the envelope theorem, and therefore, under that philosophy of the envelope theorem, the x's here, the x stars, are functions of the p's. If I had a different set of prices, I would get a different set of maximizing x stars. And if I had a different set of prices, I would get a different set of minimizing h's. So they are technically functions of the p's. So these here are functions of P1 up to Pn and the w as well. And these here are functions of P1 up to Pn and the u0 that we used. Down, he puts it at the top, doesn't he? Just to be confusing. Okay, right. And so, presumably, these two questions are related to each other via the envelope theorem.
Yeah. Slutsky's version.
Okay. So the envelope theorem says, let's just see if we've got this right. The envelope theorem says that the actual minimal E, which would be my V in the envelope theorem, you could call it E star if you want it, but then, you know, it says that if I differentiate the minimal value of E with respect to the prices or with the U0, it will be the same as the answer as if I differentiated the Lagrangian. Right. So, envelope theorem. To solve the expenditure minimization problem, you do the Lagrangian, which would be equal to E plus lambda of, like that.
So minor point, to minimize, you just maximize the negative version, don't you?
Yep.
Yeah, okay, cool.
So to solve the EMP problem, and this is a minus because plus would maximize. So that's why we've got a minus there. Alright. Cool bananas. Almost there. And then the envelope theorem says that D, E on D, P, any particular P, where E is the maximum price, minimum expenditure, in terms of P1 up to Pn and U0. Okay, the derivative of that with respect to pi is the same as the derivative of the Lagrangian with respect to pi. Is that better? Okay. And the minimum of the Lagrangian with respect to pi. Right. So the expenditure itself has a pi in it. Okay? The expenditure itself is P1x1 up to Pnxn. So let's just like that. So we've got, that's the expenditure, and I've still got the u0 minus u there. So when I do that derivative, let's see what we get. The minus will still be there. Everything other than the one with the pi in it will disappear, and the constant attached to the pi is xi. So that's where this bit comes from. The lambda is a constant multiplied on. And inside that bracket, u0 is a constant, so it will disappear. And I'll get minus u, which is the utility, which I will still have to differentiate. No? But the utility doesn't normally involve the PIs at all. So in this traditional version, I just need to go back and fix something. Traditional version of this, that's usually function of just the xi's and not the pi's. Okay, that makes sense of a lot of what's happening here. So, since the utility isn't a function of the pi's, that's 0. And so I just get minus xi. But I've lost a minus. Crap of all crap. He hasn't done it with a minus in front of it. Look at the notes.
The only thing is, the notes are one thing, and what he did in the lecture another thing, and then what they did in the tutorial was a third thing.
We don't have questions in tutorials, so we don't know.
Sorry.
We don't have questions in tutorials.
Yeah, that's another thing. Not in the question we were doing, the tutorial would have been helpful.
There is no, I know that. There is no spoon. There is no, you must, do not try to read the textbook, only try to realise the truth. There is no textbook. Sorry. From the Matrix.
Good use of it.
Because look at his, in his one here, he's come out with a plus xi in that spot just there. Just there. Which would mean over here it's the sum of pi xi is a plus.
Wait.
I did it as a minus because we were minimizing.
So did he in the lecture though?
Check.
Yeah, it was the one. Oh, was it the last one? So I thought the last one was just the envelope theorem, whereas the second one was just everybody knows the traction mapping theorem. Like, yeah.
Surely this is okay. So it's saying that E on dpi is xi, which is what you would expect by just differentiating the original thing originally. So it's saying even if you take into account choosing the correct value of everything to get the minimum possible thing, the rate of change of the expenditure is just xi. Anyway.
Rate of change.
the rate of change of the expenditure with respect to the price is just how much you buy, which makes sense.
Some shortcuts here somewhere. I'm saying it's minus 40.6.
Alright, I'm trying to do this to understand what's going on, to have an understanding of what each of the bits here are. I have a feeling I feel better about understanding it now, and we found some notes somewhere.
Like some, I don't know if this is quite right, but it looks like they're kept it positive by making the negative the lambda.
Ah, alright. So you put the lambda on the negative.
I think
So
so.
you want to keep
Maybe.
So we put actually the minus goes on the lambda if you're minimizing, not on the function.
But then because it's multiplied by a 0, it disappears, so you then you've got your positive x.
Okay. Alright.
Does that seem
I mean, I can actually know the Envelope Theorem because it's really Slutsky.
right? I wouldn't bet my house on that.
Alright. Well, I guess it sort of makes sense. The utility that you're aiming for is this one. Okay.
When you said before that it changes, the expenditure changes by the price of the piece of before. Is that going to be a positive or negative correlation?
Well, if you bought more, the expenditure should go up, so it should be positive.
So that minus x1?
Plus, because it's a positive relationship. The more bigger x1 is, the more the expenditure will be. This makes sort of logical sense. U naught is the utility that you would like to achieve, and you take off the utility you actually get, which means that if you don't have enough utility, this will come out to be a positive number, and then you're penalising for not having enough utility, which is what this minus is here.
Oh, that brings it real well.
Yeah. So if the utility is too small, you'll be penalising. If the utility is too big, you'll be actually getting extra. And normally it's the other way around. If you are maximising over here, if this over here was expenditure, if the expenditure was too small, you would get yes, you would get a positive, because that would be a good thing to not spend as much. Okay, so in the UNP it's a plus, because you're maximum. I think I get it. I have something I can say to myself to feel better about it, which is the first step to getting things. Okay, right. So that is Hotelling's theorem. Hotelling's theorem says that when you do the EMP, E on dpi is xi. Technically xi star. Because the envelope theorem says that this is because you're supposed to sub in the value of x at the maximum. Oh, no. Hi. Because we're supposed to still sub in value of xi that produces the minimum, which is actually hi. Is that, we've got something good there, James?
I was just Googling randomly, and I actually think I've just clicked, but it's not what you're doing right now.
Yeah.
I've got sidetracked,
Cool.
so please.
Okay, so let's see if we can now finally understand this Hicks-Slutsky equation. It can be shown that the compensated demand at utility U0, i.e. HI, yes, is equal to the uncompensated demand at income that. Okay. I've got it.
You read.
Well, no, I understand what happened at one step of this next thing. So this is hotellings. Okay, so one of the key things that was missing in these printed notes was that at this point he just said xi, but you have to sub in the value of xi that actually produces the minimum, which is hi. Hi is the name of the value of xi that produces the minimum. So the actual Slutsky's equation is compensated demand at utility is equal to the uncompensated demand at income. So we can say the xi at the point where so the demand, which is xi, right. So at U0 and the E that comes from U0, that's my way of saying it. His way of saying that is I'm just going to do this xi equals hi. So at U0 and the E that comes from U0 via the expenditure minimizing problem, xi is hi. So he said that as the xi P1 up to Pn E P1 up to Pn U0. So that is the xi that was found by doing the utility maximizing problem at the expenditure minimizing problem solution, right, is the same as the hi yeah. So technically that's xi star, I think. So now they're going to do the total differential. Right, we're just going to do the derivative with respect to pk. Right. Okay. So if you look at this, xi is ultimately a function of p1 up to pn and u0. What the frick? What is y? I'm to tell you what I'm looking at. So this y here,
in our case, W.
it's w. So that is the budget that we were using in the utility maximizing problem.
Yes. That's the income or the wealth or something that everything has to equal to.
Yeah, W or M or whatever we were
So-
using W for.
Yeah.
And this E has gone into the spot where the y normally goes.
Which would be the W.
Yes, or in my case, the W.
Yes.
Because you're going to spend
So when we go back to here, when we do the utility maximizing problem, somewhere, I've lost it. Aha. So when we go back to here, when we do the utility maximizing problem, that's the W there. And so technically, X star is a function of P1 up to Pn and W. Right. So this Xi here really is the star, isn't it? It's the one from the utility maximizing problem. Right. So when you differentiate something with respect to anything, if it's a function of multiple things, each of those things has to be differentiated with respect to the thing you're differentiating with respect to. So now if I differentiate this, was I doing P? Yeah. So Xi star is a function of the P's and of W, but W has E subbed into it. And so in my head I've got this picture here. Xi star is a function of both the P's and the W, but the W has E subbed into it, and so it's a function of the P's and of U naught, where U naught is a constant. Right, so if I'm going to do a derivative of this with respect to Pi, I have to do the direct derivative with Pi and go indirectly via E. But that W is really an E, right? So this is saying dxi star on dw because W is the name of the position, this position just here, and the thing that is in that position is E, so I differentiate that with respect to Pi. And this would be the same as but because of Hotelling's theorem, dE on dPi, where the E is the solution from the E is the solution, the maximal value of E based on the EMP is HI, because we just wrote that. And I just lost it too. Here. D to E on dPi is HI. So I can sub that in. That's not PI, it's PK, sorry. So D on PK of xi star plus dxi star on dw of hi k, sorry, is dhi on dpk. And that is apparently Slutsky's equation. So, what does that even mean? Have we got examples? No, of course we don't have examples of how to use this. So presumably, this is saying if you knew how one thing changed, you could figure out how the other one did?
I think this is like a link or like a bridge between the UFP and the EMP.
Yeah.
Less of a actually working a thing out and more just like a Slutsky's equation is a thing, show why.
Okay. Right. Well, we can do that now. there's a few key moments that we're missing in the notes that we have. This moment here, we call this HI. Was one of them. Right.
What are the first nesting terms? What are they links? Everything to everything.
The Roy's identity and the Shepard's algorithm.
Yes.
But there are individual links between, I think, how you can use one theory to give this links solved. It's like Shepard's to do with EMP, Roy's is to do with UMP. We prove how we can get there, and then we use it.
Basically,
See, I saw this in your notes, and I went, what does that mean?
We do too.
That's what I say every year.
and we technically didn't get the last. Oh, my handwriting's atrocious. We didn't, because we didn't get the 2 questions for the last topic. We're not really sure what would be asked.
Or how to apply it.
Yeah, like it's going to be Roy's or not.
Presumably, here's a utility function, utility maximize, and then expenditure minimize. 3 Roy's identity, 2 Shepard's lemma.
And
Show that-
verify that everything matches to everything else?
I think the 2 question had like a Cobb-Douglas of U equals x1 squared, x2 squared. Nice. And then as you go through the EMP, maximize it, and then when you get to the bottom of solving for the U, then prove you can get back to the original function with the Roy's identity. Then reverse it by doing it the other way around for the expenditure minimization problem, get to the end, use Shepard's lemma to show you can get back to where you came from. And then you do Slutsky to say that they're,
Is that what we did in the
no, this is how I understood it from the tutorial and the lecture.
Alright, so I'm really hoping that those who are watching this are not thoroughly and wholly confused, or at least not worse than you were before. I will satisfy the Hippocratic oath and do no harm, so make it not worse. I have to say that personally, I'm closer to understanding what I could possibly do. I mean, in that other example that I was trying to do, I could have done the expenditure minimization problem, because technically I did the utility maximizing problem, and then all of the solutions should match up via these Slutsky's equations and things. That's what it's trying to tell me. Okay. So Roy's equation, Roy's identity, apparently this.
Yeah, that's Roy's identity. If you apply that...
Is that xi star, probably? Probably.
Yeah. If you apply that to the indirect utility function, you'll get back to the xi star.
Yeah.
And so, which we would call ordinary or already in demand. And if on the other side you take the expenditure function, which is what you get when you plug in the optimal h's into the expenditure function, and you apply to the expenditure function.
This is Hotelling's lemma.
Yep.
Hotelling's theorem.
Which we just did.
Wait, that's Hotelling's?
Here.
Yeah.
That is Hotelling's?
Yeah.
I'm going to kill Maverick.
No, we just wrote Hotelling's.
Yeah,
Right?
I know. But no.
See, look,
because-
Hotelling's. DELDPI comes out to HI.
Oh, yeah.
So we just did it.
A friend of mine with like certainty was like, that is Shepard's lemma. Like, that is... That is... I didn't even text it.
Okay, so
Alright.
where's the Shepard's in work? Because I remember
So which one?
Yeah, we should
Dimitri
do
talked about Shepard's lemma as well.
Yeah.
Alright, well, how is Shepard's really spelt? Because it's not finding it in here.
Check notes.
So that's... Can you please just scratch out Shepard's point? Just...
But Shepard's goes there. You just don't have Shepard's on.
No, but...
Shepard's lemma is the link.
So wait, that hi equals the derivative of the exponential function with respect to the I.
Which
That
notes
is-
is this one?
I don't know. But that is how you get from the expenditure function back to fixing demand. Yes?
Yeah.
Cool. So Shepard's lemma is a thing, but it's not there. Is that correct?
That's what I think.
So
The phrase Shepard does not occur in these notes.
Might be the same as the other one.
oh, you mean it might be the same? Okay.
So,
I'm looking
I guess
Shepard's.
it's a...
it goes back to the weird strokes thing.
Yeah, what I have for Shepard's lemma seems to be which is Hotelling's.
So Shepard's lemma is the same as Hotelling's theorem.
Possibly, but you've got a set, you've got any possible peaks, but you've got a set point for
Yeah, that's the U norm. That was in the other thing,
Yeah.
which is now apparently U bar.
So they're the same thing.
So apparently they are the same thing.
Yay! Yay!
And then I
Okay. Alright, so that would mean that we could therefore have go through with my example and we could conceivably do all of these derivatives that we're seeing and actually come up with everything being correct and matching them all up. So before I did, in my example, I got to dl on dw being something which is the same as dv on dw, and apparently according to Roy's identity, which I haven't mentioned up till now, but I'm just thinking about. So Roy's identity is apparently, according to these notes, that. According to these notes here. Yours, these belong to.
Thank you.
Okay, so we could, back in my other example. Sorry. So back in my other example, I already did dv on dw. Which was this here, that there. Okay. Whoops. And I could do dv on dp1 So I have a choice on how to do dv on dp1. I could either go back to whatever v was, which is this, and differentiate that with respect to p1. Alternatively, I know that dv on dp1 is the same as dl on dp1 because of the envelope theorem.
Is it DP1 or is it DPI? We have to do it.
Oh, we'd have to do it for both, but I'm just checking one of them.
Oh, right, okay.
I'll just do I equals 1. So I could literally differentiate v with respect to p1, or I could differentiate L with respect to p1, and they should come to the same answer. Yes, but I might do this one. 3 3/4 W. I'm just going to type P1 to the -1/4 on the side there. I'm just rearranging what V looks like so that I can bring the P1 out by itself as a power, because then I can go, well, all of this is a constant multiplied on. And P1, the power will go down by 1, which will be now at 5/4. And I'll times by the original, so times by the original power, and the power goes down by 1, that is dv on dp1. And Roy's identity says that that ought to, that dv on dp1 over dv on dw, but minus should come out to xi. Let's see. So that will be this thing divided by this thing with a minus. And let's see. Well, this bit is the same as all of that crap, except for the W. Like all of this is all that stuff there. So like that cancels with that. I think. Have I done something wrong there? Because X I star totally didn't have a 5/4 in it. Oh, look, there's a P1 here, sorry, don't cross that out, it's still there. Right, thank you, good notice. So that minus will cancel with that minus. And so I now have, just for, let's see, we have a W and a P1 to the minus 5 on 4. And on the bottom we're left with a 1 over P1 to the quarter. So the 4 cancels with the 4, the 3 to the quarter cancels with the 3 to the quarter, the P2 to the 3/4 cancels with the P2 to the 3/4. Alright. And there's still a quarter here, isn't there? Ah. Right. Alright, they're all the bits that haven't cancelled out. And so, let me just do one more thing. That was a P1. So P1 to the quarter on the bottom of a fraction is P1 to the minus quarter. 5/4 minus a quarter would be 4/4, which would be 1. Which is W, a quarter of W to the minus 1. So minus 5/4 minus a quarter would be minus 5/4 plus a quarter, which would be minus 4/4, which is minus 1, which is W on 4P1, which if we were very paying close attention to the example that I did, X1 star was W on 4P1 and the world makes sense. Right.
One question that is.
Okay. My feeling, my instinct, is that if he's going to, so I don't know, if I was going to construct a course where you learn to do this stuff, I would sort of get you to figure out some of them and then use Roy's lemma to figure out something else. I could go figure out this, and now that you've got Roy's lemma, figure out this. But, rather than getting you to figure out everything and subbing it in, but I have a feeling that he may just ask you to figure out everything and verify the various lemmas and theorems by subbing everything in and showing that it comes out to the same answer. That's my instinct. Is that what happened in the tube?
We don't know anything about the question.
Okay.
The answer.
But I had the slightest hope now that I could get some marks for that.
Well, that's one of us.
Well, I mean, Lagrange multipliers you've done before in other courses, and you could solve you could do a utility maximizing thing because you've done that before. At the very least, you can do that, and then the idea is that you can say, well, the maximum value is equal to this, x1 star equals this, x2 star equals this, lambda equals this, and then you could conceivably do the same thing for the other one, and you get h1 equals this, h2 equals this, lambda equals this, and then you could conceivably do all of the derivatives and make them line up, as long as you knew what the actual theorems were. So you don't necessarily need to be able to prove them, but I don't know if you need to or not. I'm sorry. But I think I have a handle on the envelope theorem now, at least for this sort of thing. If I was going to try and tie this up in the last few minutes, and I will talk about the contraction method theorem anyway. If I was going to try and tie this up, I would try and draw a diagram roughly like the one that you had. but with more colour coding. So,
I feel like an electronic one in some other semi, which is a lot better.
yeah, and it seems to me that it's actually all connected via those two problems. So you've got your utility maximizing problem and your expenditure minimizing problem. You've got a utility which is a function of the x's, and an expenditure which is a function, well, we know what expenditure actually is. Like that. And that's what we have. They're both, in fact, even before that, I would cross them out. We have both of these things. The utility maximizing problem is maximize u subject to E equals a particular answer. The expenditure minimizing problem is minimize E subject to U is a particular answer, also known as U bar in the notes, and this W is a Y in the notes. So that's what they are. And the key to it for me was understanding that the solutions to this are like x1 equals x1 star up to xn equals xn star, and these are functions of the p's and the w. And the solutions to this are x1 equals h1 up to xn equals hn, and these are functions of the p's and u. No. That's very bad writing, I'm sorry. And to me that's the key to all of it, that
So what's the last thing you said?
functions of the p's and u naught. Here, functions of the p's and w. So, and then we've got all these equations which relate the derivatives of various things with respect to the derivatives of various other things. So Slutsky's is actually about using the solution to this over here. So Slutsky's is saying we use the solutions to the EMP over here in the UMP, and we can figure out what various derivatives are. And Roy's is about just the solutions of this. He's saying these solutions here, how are they related to the original P's? Yeah. Right. Well, if I come up with something in the next couple of days, I will add it to the page. As I work with you guys, I will add it to the page. This will go on the website. I'm actually going to stop the recording and do the contraction mapping theorem in its own recording, so it's easier to find.